my goal for you in this video, what I want you to be able to do when this video is over, I really just want you to have an awareness in the back of your mind that sine and cosine are pretty amazing functions, and there are a lot of formulas and identities that apply to those functions. And I want you to at least have enough of a vague memory of these formulas to be able to Google them and look them up on the rare occasion that you might need them. That's the goal really for today. The first set of identities that hold true for sine and cosine are called the sum and difference identities. And these sum and difference identities are designed primarily to help you to take either sine of a sum of two angles or cosine of a difference of two angles, and to break that quantity down in terms of sines and cosines of the two individual angles that are being added or subtracted. To give you a brief example of how this can be useful on occasion, suppose that you are required to give the exact value of sine of 75 degrees. Now, the word exact has a very specific mathematical meaning. Exact means that there had better not be a decimal point anywhere in your answer. Exact means that no rounding is allowed and decimals are not allowed. So as a result of that, for most calculators, this means that you probably won't be able to answer this question using a calculator. If, say, I wanted to use the Windows 10 scientific calculator to answer this question, then first I would check I was in degrees mode, then I would type in 75, and then I would apply sine to it. But as you can see, this answer is given in terms of decimal number, which is forbidden based on how this question is phrased. And you'll run into a similar problem if you're trying to calculate this value using a TI-8384 or something like that. Instead, what we can do is apply one of the formulas above to rewrite 75 degrees in terms of angles which show up on our reference circle. For example, 75 degrees, 75 is equal to the sum of 30 degrees and 45 degrees. And what's nice about 30 and 45 is that these two values show up on our reference circle image. And therefore we can find exact values of both sine and cosine at 30 degrees and 45 degrees individually. So looking at the list above, the formula that helps me to deal with sine, where the sum of two angles is in the input, is this formula here, this third one, which says take sine of your first angle, multiply it by cosine of your second angle, and then add cosine of your first angle, and multiply it by sine of your second angle. Now my unit circle reference image tells me that sine of 30 degrees is equal to exactly 1/2. And it tells me that cosine of 45 degrees is equal to exactly root 2 divided by 2. It says to me that cosine of 30 degrees is equal to exactly root 3 over 2, and sine of 45 is equal to exactly root 2 over 2. And therefore the entire quantity, if I simplify this a little bit, would be equal to root 2 over 4 plus root 6 over 4. These two fractions actually have the same denominator, so it would be possible to combine this even further, root 2 plus root 6 over 4. This would be the exact value of sine of 75 degrees, a value that has not been rounded at all and does not involve any decimals. The upshot of exact values is that you are leaving it to the reader to round whenever they want to to however much accuracy they need for their problem. If you handed this value to a construction worker, they might round it to 1 decimal place. If you handed this value to a physicist, they have the option to round it to 10 or 15 decimal places. You can give this value to anybody and they could use it for any purpose without worrying that accuracy has been lost. Alright, the half-angle identities. So the half-angle identities are telling you what you can do if you have cosine of half of an angle. This has applications which are kind of similar to the very first exercise that we did today. This can be used to help us find exact values of sine and cosine at certain tricky angles. Find, for example, the exact value of sine of negative pi over 12. Now it says exact, which means that decimals are not allowed, which means that most calculators are not allowed. However, this angle, pi over 12, does not appear on most unit circle reference images. How therefore would I address a problem like this one? Pi over 2 is exactly half of negative pi over 6. And negative pi over 6, aka negative 30 degrees, is one of those values that shows up on a unit circle reference image. This, for example, would be coterminal to positive 330 degrees. Now the half-angle identity says, alright, you're interested in sine of half of an angle, let's call it theta. Then the result is equal to either the positive or the negative square root of 1 minus cosine of the angle theta, the angle before it was cut in half, all over 2. Cosine of negative pi over 6, cosine of negative 30 degrees, was equal in value to square root 3 over 2. So the exact value of sine of negative pi over 12 is equal to either the positive or the negative square root of this number, which I will simplify to 1/2 minus root 3 over 4. Now question, is it going to be the positive square root or is it going to be the negative square root? Which one is the correct final answer here? To answer that question, let's consider the quadrant into which the given angle is pointing. Negative pi over 12, which can be converted to 15 degrees. Because it's negative, it points into quadrant number 4. And as a result of that, the y values, the sine outputs, will all be negative. Therefore, the correct final answer to this question would be the answer that has the negative square root only. This quantity, the negative 1/2 minus root 3 over 4, is the exact value. There is another collection of identities, properties that are satisfied by sine and cosine. And these properties occasionally actually are useful in calculus too. In calculus, a general principle is that products are difficult to work with, whereas sums and differences are easy to work with. So in calculus, any formula that allows you to transform a product into something that just has plus or minus is really valuable. For example, in this exercise, we have the product of sine of x and sine of 3 times x. Now, the formula that looks the most applicable to my situation is this second one in the list here, which is describing me how to take a product of 2 sines with 2 different types of input and rewrite it as a difference of cosines. This formula says take 1/2 of cosine where the input is equal to the first angle minus the second angle. The first angle in my first sine is x. The second angle in my second sine is 3x. Then take away cosine. This time add your two angles together. So the angle in sine is equal to x and the angle in the other sine is 3x. So this would be equivalent to 1/2 cosine of negative 2x minus cosine of 4x, where the half is being applied to the entire quantity or to both of the cosines. Compared to the previous expression that we started with, this would be much simpler to work with in Calculus 2. We have the power reduction identities. Now, we mentioned a little while ago that in calculus, products, when two things are multiplied together, that's a huge annoyance usually to work with in calculus. And because powers, like sine to the fourth power, are just a compactified way of writing a potentially quite magnificently large product, powers are also often quite difficult to work with in calculus. Everything except for the most simple power are often quite difficult to work with in calculus. So these formulas actually do come in handy quite a bit in calculus 2 and 4 as a way of eliminating powers from expressions that contain sine and cosine. For example, here we are given sine to the fourth power, and we are asked to rewrite this so that it has no powers in it. Now, sine to the fourth power does not appear on either side of either one of the power reduction identities. However, using the properties of exponents, I can rewrite sine to the fourth power as sine squared, quantity squared. If you square something and then square it again, then in total you're going to get 4 copies of that factor. So x squared squared is equivalent to x to the fourth power, and likewise sine to the fourth power is equal to sine squared squared. Now let's work on this sine squared on the inside for a second. The power reduction identity tells me that sine of something squared is equal to 1 minus cosine of 2 times that something all over 2. So let's simplify this expression, 1 minus cosine of 2x all over 2, quantity squared, which is equal to 1 minus cosine of 2x, quantity squared, divided by 2 squared, which is equal to 4. Now, I'm going to use the algebraic formula that says if you subtract two things and then square the difference, then that's equivalent to a squared take away 2 times a times b plus b squared. I'm going to apply it to this quantity here in the numerator. Instead of a minus b, I have 1 minus cosine. So that is equivalent to 1 squared minus 2 times 1 times cosine plus cosine squared. And that's all over 4. So let's simplify what we have. Instead of 1 squared, I'm just going to write 1. Instead of 2 times 1, I'm just going to write 2. And then we have the cosine squared in the back. All of this all over 4. Now, we're a lot closer than we were before. I mean, we got rid of the power of 4, but as a result of doing that, we have now introduced a power of 2, this time on cosine. So if we want to obey the instructions rewrite this without any powers, we are also going to have to get rid of this square on the cosine in the back. So to that end, I'm going to try and position myself so that I can use this formula here, which tells me what to do with cosine squared of something. The first thing that I'm going to do, though, is I'm going to try and rewrite this as 1 over 4 minus 2 over 4 cosine 2x plus 1 over 4 cosine squared of 2x. And this is just so that I can look at cosine squared a little more closely here on the far right side. The identity says that if you have cosine squared of something like 2x, then take cosine and double that something. So if 2 is already in the parenthesis, and I need to double what's in the parenthesis, then that's going to become 2 times 2x plus 1 all over 2. So in total, cosine of 4x. Now cosine squared is equal to cosine of 4x plus 1 all over 2. That was in the expression with a 1/4. This 1/4 in the front, and I'll reduce this fraction to 1/2. This is equal to sine to the 4th power of x. Now, although it looks a lot more complicated than what we had before, this would be leagues easier to work with in calculus than sine to the 4th power. That is how annoying powers are in calculus, that something like this would be much easier to work with than what we started with, because it has no powers in it. Set of identities that can be quite useful is the set called the double angle identities. One of the primary applications of this identity in the front is to help take a product of sine and cosine and transform it into a very compact sine of a single angle. Let me give you a problem from physics. In this case, we have an object which is being launched with an overall speed of 70 meters per second. Now that's the speed of the object, but what we don't know right now is the angle of inclination of the launch. That's just being represented by a variable currently called theta. Now in physics, you develop formulas to help you predict the position of the object after a certain amount of time. The object's horizontal position, how far it's made it in the x direction, which here is being called h of t for its horizontal position at time t. And there is another formula from physics to help you predict the object's vertical position. And in the case of a velocity of 70 meters per second and a launch angle of theta, those formulas are given here. The object's vertical position, its height above the ground, can be found by taking the speed of 70, multiplying it by sine of the launch angle, and multiplying that by the number of seconds that have passed, t in this case, and then subtracting 4.9 times t squared. This is what accounts for gravity. This is the gravity term that reflects how the object is being pulled back down to the ground by gravity over time. The formula for the object's horizontal position, t seconds after it was launched, is given by this formula: h of t equals 70 cosine of theta multiplied by t. So it's a little bit simpler. Just take the speed, multiply it by cosine of the launch angle, and multiply it by t. So now suppose that we're setting up our catapult, we're setting up our trebuchet, with the goal of launching an object so that when it falls back to the ground, its 800 meters from its initial position. So the question is, if I am able to shoot this object with a velocity of 70 meters per second, how should I angle the launch? What should theta be to achieve this end? That way, if you're trying to, siege somebody's castle, you are able to actually hit their castle walls and...
Now, let's see how strong those walls are.
Let it rip!
That was just the first shot. The trebuchet has to be calibrated. That's perfectly doable.
So to answer this question, the thing that I'm going to do is this. Both the horizontal position formula that I have and the vertical position formula that I have are given in terms of the time t. So the first thing that I'm going to do is I'm going to find the time t when the object actually hits the ground. I'm going to find out at what time the object is intended to strike this object here 800 meters away. At what time? Then I'm going to try and find theta, so that at this time, when the object hits the ground, the horizontal position at that moment is equal to that 800 meters. In step number 1, by finding the time when the object hits the ground. In other words, I'm going to find t when the object's height above the ground, its vertical position, is equal to 0. Now I'll take our vertical position formula, which is 70 sine of theta multiplied by t minus 4.9 t squared equals 0. And let's work on isolating t in this expression. The first thing that I notice is that both of these terms on the left contain a t, and therefore t can be factored out. Factor t out of the second term, and this is what needs to be equal to 0 in order to find the time when the object hits the ground. Now, based on zero product property, there are two possibilities. One is that t itself is equal to 0, but this answer isn't useful for our purposes right now. T equals 0 would be when the object was first launched, so it's not helping me to figure out when the object is intended to hit its target 800 meters away. Not useful. The other possibility is that the other factor, 70 sine of theta minus 4.9 t is equal to 0. So let's take this expression and isolate t. Again, we're trying to find the time. We're trying to find t when the object's vertical position is 0, because that's when the object will have hit the ground. So, for example, if I move that 4.9 t over to the other side and divide both sides by 4.9, I find that the time when object hits the ground, 70 times sine of theta, this expression on the left, divided by that 4.9. Now the time it will take the launched object to return to the ground is going to be dependent on the angle theta at which the object was launched. If you launch the object high up into the air, it's going to take a long time to come back down. Whereas if you launch the object so that the angle is quite shallow, it won't take nearly as long for the object to fall. That's why our answer for the time contains a theta. There's nothing we can do about that right now, so let's move on to part 2. The goal is that at the time t, when the object hits the ground, h of t is equal to 800. We need h of t, whose formula was given by 70 times cosine times t, to be equal to 800. Now, because we're specifically interested in the time when the object hits its target, and we found that the time when the object hits its target was given by this expression, we can substitute this expression in for the t in our horizontal position. So now what do we have? We have 70 times cosine of theta times 70 sine theta over 4.9. That is what needs to be equal to 800. And our goal is to figure out the angle theta that will make this possible. Let's begin by cleaning this up a little bit. If I take 70 times 70 and divide that by 4.9, that turns out to be equal to exactly 1000 times cosine of theta times sine of theta. That needs to be equal to 800. Dividing out 1000, then I get cosine theta times sine theta is equal to 0.8. Now, some of you with very good memories may be thinking back to the video where we were solving trig equations of a more complicated nature that looked like this, where we had sine of x multiplied by cosine of x equaling 0. In that case, we were able to use zero product property to split this equation into either sine of x equals 0 or cosine of x equals 0. But the problem is that in our equation, what we are lacking is the zero part of the zero product property. Our product, sine times cosine, is not equal to 0. Our product is equal to 0.8. So zero product property cannot be used. So how are we going to figure out the values of theta that make this equation true? The identity that's going to come to our rescue is the identity right up here, which says that if you have 2 times sine times cosine, then that's equal to a single sine with the 2 in the input. Now our expression is pretty close to what is on the right-hand side of that identity. We have the sine multiplied by the cosine, but we do not have the 2. So let's multiply both sides by 2 to get that in there. So now we have 2 times cosine times sine is equal to 1.6. We get that sine of double the angle theta is what needs to be equal to 1.6. But notice something. What we are requiring is that sine output a value that is larger than 1. So during our solution process, we ran into something that was mathematically impossible, and that was proof that our catapult cannot hit an object 800 meters away. So you would need a more powerful catapult, or you would need to move the object closer to its target. Pretty amazing. that we are able to take these two physics formulas and a little bit of trig knowledge and deduce that no matter how you try and calibrate this catapult, you're not hitting that thing that's 800 meters away. That concludes today's material. Today we introduced the double angle identities and the power reduction identities, both of which are fairly useful in Calculus 2 and Calculus 4. The double angle identity can also be used in situations where you're trying to solve a trig equation that has a cosine multiplied by a sine equals a non-zero number. For example, in this pretty cool physics problem, we were able to use that identity to figure out that the catapult in this problem could not reach the object which was located 800 meters away.